Hey, thanks for joining me in class today. We're going to be learning about properties of logarithms today, and there is a warm-up. So please pause the video now and complete the warm-up. When you've completed it, tune back in and we'll get started learning about properties of logarithms. So thanks for trying the warm-up. Take a moment and check your answers to each of the questions. So in the warm-up, you were asked to apply some of the properties of exponents that we just recently reviewed. For instance, in question number 1, you had to multiply two bases that were the same, and to do that, to combine them as a single exponent, you had to add the exponents. It'd add the -2 and the 5 to get 3. So the result was 3 to the third power, or 27. In the second one, you had to apply the quotient property, which says you have to subtract the exponents when you divide two bases that are the same. In number 3, you were raising a power to another power, and we know that to do that, you have to multiply the exponents. In questions number 4 and 5, I ask you to apply what we learned in the prior lesson to convert from what's called logarithmic form to exponential form. And when we do that, basically a logarithm is an exponent. It's just another way to write an exponential expression or equation. And so in the case of number 4, we start at the base here, and since a logarithm is an exponent or a power, then on the other side is the power. So the power is 1. So it's base to the power equals the result, and so x to the first equals x. And the same thing applied in number 5. So in today's lesson, here are our learning goals. We're going to use properties to simplify logarithmic expressions. And we're actually going to see that the properties we learn about logarithms are directly related to the properties we already know about exponents, because a logarithm is an exponent. And our second learning goal is to translate between logarithms in any base. So we'll see if we can maybe take some logarithm that's in a certain base and switch it to a different one. So now the big focus in today's lesson is to apply what we already know about exponents and their properties. For instance, the product rule for exponents, and see how that relates then to the logarithmic properties. So recall that to multiply powers with the same base, you just simply add the exponents. So here's a restatement of that property that we learned in a prior lesson. Now the log rule that goes along with that exponent property is called the product property. And basically what it says, and I sort of read it backwards, I read the right hand side first, it says the log base b of m plus the log base b of n is equal to the log base b of the product of m and n. And so basically what it's saying is if you have two separate logs with the same base, that you can combine them together by multiplying their results. And so here a quick example of that probably kind of makes it a little clearer. So I know that if I had the log base 3 of 2 and the log base 3 of x, I could combine them together and I could write it as a single logarithm, log base 3 of 2 times x. So in other words, when you're multiplying two bases that are the same, you add the exponents, that's the exponential property, and when you're adding two logarithms with the same base, you multiply the two results. So that's the connection there. Because a logarithm is an exponent, the properties are related there. Let's take a look at applying that logarithmic property. So it says express the log base 6 of 4 plus the log base 6 of 9 as a single logarithm. Now why would we ever want to do that? Well, here's the reason why we need to know these properties. If I try to express the value of log base 6 of 4, I'm trying to think of 6 to what power is 4? Well, I know 6 to the first is 6, so it's obviously something less than 1, but I really have no idea what the value of the exponent would have to be to raise 6 to that power and get 4. And the same thing goes with if I looked at the log base 6 of 9. Because I don't know what I can raise 6 to get 9. I know it's something greater than 1 because 6 to the 1 is 6, so it's got to be bigger than an exponent of 1, but I don't know how much bigger. But when I use this log rule to combine these, this is what it would look like. So the log base 6 of 4 plus the log base 6 of 9 could be written as a single logarithm, log base 6, of the product of 4 and 9, which is 36. And now if I wanted to evaluate the log base 6 of 36, what I'm actually asking is, what power would I have to raise 6 to get 36? And hopefully that's clear that that would have to be 2, because 6 squared is 36. So by being able to combine those logarithms together, I was able to get something that I could actually evaluate, find the value of. Let's go ahead and turn the page and look at some more examples. So the directions say to express as a single logarithm, so we're going to combine these using that product rule, and simplify if possible. So when I look at the two bases of these logarithms, they're the same. So the base of both of these is 5. So I could combine these together as a single logarithm, and if I did, it would look like this: the log base 5 of 625 times 5. So I went ahead and put that in my calculator, and I got 15,625. So what this is asking me is, if I wanted to then find the value of this, is I'm trying to find out 5 to what power is going to be 15,625. Well, it's going to have to be a fairly big exponent. I mean, it can't be 2 or 3 or 4. It's going to have to be larger than that. So really my best bet would be just to guess and check and just try to pick values and plug in and raise 5 to those powers and see if I get this 15,625. So in this case, it might have been more advantageous to actually just keep these separate, because this is, when I look at the original, the log base 5 of 625 means I want to know 5 to what power is 625. And that might be one that's pretty easy to find. I know that 5 squared is 25, 5 to the third is 125. If I multiply by one more 5, that would give me 625. So I know that that would be 4. And if I did the same thing with the next one, so now I look at the log base 5 of 25, well, I know 5 to what power is 25. Well, that's pretty clear that that one's got to be 2. And so the log base 5 of 625 plus the log base 5 of 25 is actually equal to 6. And if I went back over and I tried this one now and I said, okay, well, let's see if that's what I would have gotten doing it the other way. I know that 5 to the 6th power, if I plugged it in my calculator, would give me this 15,625. So in both cases, I was able to find that the value was 6. It's just that one way might seem easier because you're dealing with smaller powers of 5. So you can use them either direction. I mean, you don't necessarily, in some cases, have to combine them to be able to simplify. Some cases it makes it easier, and some doesn't necessarily help it too much more than if you just did it the straight up way, looking at the logs separately. Okay, so how about example C? So this time it's the log base 1/3 of 27 plus the log base 1/3 of 1/9. Well, let's say I put these together as a single logarithm, so I'm going to multiply the results. So I could rewrite this as the log base 1/3 of the product of 27 and 1/9. If I multiply 27 and 1/9, I get 3. And so what I'm asking is, what power would I have to raise 1/3 to, that's the question mark, to get 3? Well, hopefully that one's obvious, that one is -1. If we were to raise 1/3 to the -1 power, that -1 means to flip that. And if I flipped 1/3, I'd get 3. And this little caution here just really emphasizes the fact that if you're going to be combining logarithms, just like if you're trying to combine when you're dealing with the exponent rules, the bases have to be the same. So you have to have the same base to be able to combine them. All right, so let's take a look at the next property. So you may remember, hopefully, since we just applied it in the warm-up, the quotient property for power. So when you divide two bases that are the same, you subtract the exponents. Well, there is a related log rule as well. So the related log rule says this, it's called the quotient property, that if you are subtracting two bases that are the same, two logs, with the same bases that are the same, you can combine them together as a single logarithm by dividing the results, the m and the n. So that would be a way of, if you are subtracting two logs of the same base, to combine them and make them a single log by just simply dividing the two results, m divided by n. So here's a little example. The log base 2 of a half, it would be equal to the log base 2 of 1 minus the log base 2 of 2. Now that's a way of looking at it in one direction. The way we are usually going to be using it is to combine, so looking at it going this way instead, where we'd say we have two separate logs being subtracted, the log base 2 of 1 minus the log base 2 of 2, and we combine them to rewrite that as the log base 2 of 1 divided by 2, or the log base 2 of a half. Let's take a look at some examples. So it says express as a single logarithm and simplify if it's possible. So again, kind of just thinking about why we might want to use this. If I were to ask you to tell me the value of the log base 5 of 100, I'm thinking 5 to what power equals 100? Well, I know 5 squared is 25 and 5 cubed is 125, so it's got to be somewhere between 2 and 3, but you know, that's not pinpointing it very closely. So being able to keep these separate and simplify is going to make things difficult, but when I combine them using this quotient rule, this is what it would look like. I could rewrite this as the log base, well they have the same base so that I can combine them, 5 of the quotient between 100 and 4. And so when I then simplify that, it would look like this, log base 5 of 25. Now that's pretty easy, because now we're saying what power would we have to raise 5 to get 25, and clearly that's 2, because 5 to the second equals 25. Let's maybe make this next one a you-try question. So see if you can try this one. This one seems like a pretty easy one. First combine the two logarithms into a single logarithm, and then simplify if possible. So pause the video now and give this one a try independently. Okay, so the answer to this one turned out to be 1, because when you combine them, you were able to write it as a single log base 7 of 7, and we know that 7 to the first power equals 7. Let's go ahead and turn the page. Okay, so next we're going to look at the power property for logarithms, and if we think back and look at the exponent rule that's related, the power of a power property, this is what the power of a power property said. It said when you raise a single base to two exponents, so when you raise a base to another base, you multiply the exponents. So here's what the power property for exponent says. Now what about the power property for logarithms? So since a logarithm is an exponent, it really does say the same thing, but just in a little different way. So what it says is if you have a logarithm, which by the way is an exponent, and it's raised to an exponent, you can rewrite it as a product of the exponents. Well, remember that this part right here, this logarithm, that's an exponent, and then this part right here, well, that's another exponent. And so we can rewrite it as a product of that logarithm, log base b of a, and the power, which is another exponent of p. And basically we do that by just bringing that p down in front and basically turn it into a coefficient. But really it means we're just multiplying that power by the other power, which was expressed as a logarithm. So the log base b of a to the p power becomes p times the log base b of a. So simply just bring that power down in front and it becomes a coefficient. And I think by looking at some of these examples you'll see why this is really an important property. So it says express as a product in example 3 and simplify if possible. So let's think about if we didn't know this property, what we would have to do. So they want to know what log base 2 of 32 to the 6th power is. So we're actually looking for what number we could raise 2 to get 32 to the 6th power. Well, wow, well, first of all, 32 to the 6th power, that's a very large number. And so to try to evaluate that, I mean, I'd be all day thinking what powers I can raise 2 to get 32 to the 6th power. I mean, 32 to the 6th power, I don't have my calculator handy, but I'm sure it's a very, very large number. So instead, if I apply this property to write this as a product and then simplify, this is what it would look like. we'd bring this little 6 down in front, and it becomes a coefficient. And so when we rewrite it, it would look like this: 6 times the log base 2 of 32. Well, that's pretty easy, because I think about the log base 2 of 32, I'm thinking 2 to what power is 32? Well, that's one I kind of commonly already know. I know that 2 to the 5th power is 32. So this is really just saying what is 6 times 5, because this part of it, this log base 2 of 32, is 5. And so the answer to this is 30. So if we raise 2 to the 30 power, we'd get the same thing as if we raise 32 to the 6th power. So feel free, if you have your calculator handy, to verify that. So the actual answer to our question is, we first wanted to rewrite this as a single logarithm, and then we wanted to find the value. So let's kind of rewrite this in the correct answer. So we write this as 6 times the log base 2 of 32, and it's equal to 30. So this is what our final answer should look like. Let's take a look at another example. So in B, again, we want to know 8 to what power would be the same as 4 to the 20th. Well, that's very large, so that's going to be difficult to do. So I'm going to bring this out in front. I rewrite that as 20 times the log base 8 of 4. And now I got to think about if I can simplify this. So I got to look at this log base 8 of 4 and think, is there some really easy fractional or integer power of 8 that I can raise it to, or raise 8 to get 4? And I'm not thinking of one. I don't think there is one that's a nice value. And so this is one that we would just not simplify. Notice it does say only simplify if possible, and so this is the best we can do. We'll just leave this as our answer that was written as a product. And remember, we can't really use our calculator to help us here. We can only do that if we're using the common log or base 10 log, which turns out that that's what our next example is. So the first thing on C I want to do is rewrite this as a product. So I'm going to take that power that's a 4, bring it down in front, rewrite this as 4 times the log of 10. Well, remember, this is base 10. If there's not a 10 written, if there's not a base written, it means 10. And so to simplify this, I know I just have to figure out what the log base 10 of 10 is. Well, that's easy. If the base is 10 and the result is 10, the power must be 1. So this is really just 4 times 1, which is 4. So my answer would be 4 times the log base 10 of 10, and that's equal to 4. How about the example D? So again, we're going to rewrite this as a product. So we bring the 2 down in front, so it's 2 times the log base 5 of 25. So that really means that because log base 5 of 25 must be 2, because 5 to the 2nd power is 25, this really means 2 times 2, which is 4. So the value of log base 5 of 25 squared is 4. And that means if I raise 5 to the 4th power, I'd get the same thing as if I raised 25 to the 2nd power. And I think we get the point. So we'll go ahead and we'll skip example E and move. Okay, so we've learned quite a few properties today, and that's a lot to take in, a lot to process. And so we're going to end our lesson today at this point, and we'll pick up where we left off for the next lesson. And so make sure you take note of any of the things that you've not quite picked up on yet, things that you have concerns about, and we'll be sure to talk about those things when I see you in class.